Until now, we've been looking at Euclidean geometry. Now we're going to explore beyond Euclidean geometry. This is section 10.7. The objective, gain an understanding of some of the general ideas of other types of geometries. The first thing we're going to look at is the geometry of graphs. The Swiss mathematician Leonhard Euler proved that it was not possible to stroll through the city of Königsberg, Germany, by crossing each of 7 bridges exactly once. His solution opened up a new kind of geometry called graph theory, and this little box below shows you a map of the city and the bridges. These are some graph definitions. A vertex is a point. An edge is a line segment or curve that starts and ends at a vertex. The graph consists of vertices and edges. An odd vertex has an odd number of attached edges. An even vertex has an even number of attached edges. This leads to the rules of transversability. A graph can be transversed if it can be traced without lifting the pencil from the paper and without tracing an edge more than once. A graph with all even vertices is transversable. You can start at any vertex and end where one began. A graph with 2 odd vertices is transversable. You have to start at an odd vertices and finish at the other. A graph with more than 2 odd vertices is not transversable. Example 1, to transverse or not to transverse. A, is this graph transversable? You begin by determining if each vertex is even or odd. This particular one has 2 odd vertices, so by the second rule, it is transversable. You can describe the path to transverse it because by the second rule, you start at one of the odd vertices and you finish at the other. Next, topology. This is the study of shapes. Objects are classified according to the number of holes in them, called their genus. Genus is the number of cuts that can be made in the object without cutting the object in 2 pieces. Topologically equivalent objects have the same genus. The topology of knots is used to identify viruses, and how they invade our cells. This shows some examples of topological equivalency. The 3 shapes below in pink have the same genus, 0. No complete cuts can be made without cutting these objects into 2 pieces. A donut and a coffee cup have a genus of 1. Next, we have the Klein bottle. The figures below show the transformation into the figure called the Klein bottle. Because the inside surface loops back on itself to merge with the outside, it has neither an outside nor an inside. It passes through itself without the existence of a hole, which is impossible in 3-dimensional space. It only exists when generated on a computer. Now we're going to compare 3 systems of geometry, Euclidean and non-Euclidean. Euclidean geometry in the first column shows that given a point, not a line, there is one and only one line through the point that is parallel to the given line. Geometry is on a plane. Hyperbolic geometry, given a point, not a line, there is an infinite number of lines through the point that do not intersect the given line. Geometry is on a pseudosphere. And elliptic geometry, there are no parallel lines. Geometry is on a sphere. More comparisons. For Euclidean geometry, the sum of the measures of the angles of a triangle are, or is, 180 degrees. Hyperbolic, the sum of the measures of the angles of a triangle is less than 180. And elliptical geometry, the sum of the measures of the angles of a triangle is greater than 180. Finally, fractal geometry, and some of this is used by artists to create artistic works. It was developed using computer programming. It's the geometry of natural shapes, and we're going to be given two definitions here. Self-similarity is a quality of similar versions of an object appearing in the object itself, as you can see on the leaf. Iteration is a process of repeating a rule again and again to create a self-similar fractal. And that concludes this lesson.